In this video, I would like to introduce two special right triangles that we use frequently to evaluate common trigonometric functions. First, I'd like you to consider a square. We know that the angles here are right angles and that all of the sides of the square are the same length. We'll call that S. If I drop a diagonal across this square to form two triangles, I now have a 45-degree angle in each of the corners because I've cut the 90-degree angle in half. I can use the Pythagorean theorem to find the missing side, the hypotenuse of this right triangle. I have s squared plus s squared equals blank squared, or 2s squared equals blank squared, and when I take a square root, I have that this blank equals the square root of 2 times s. So the hypotenuse is the square root of 2s. Now, when I evaluate sine, cosine, and tangent on this 45, 45, 90 triangle, because all of the sides are multiplied by this factor of s, the side length, sine, cosine, and tangent will be the same for any given side length. So it is often convenient to simply express this triangle with a side length of 1. Then we arrive at the sides 1, 1, square root of 2 for a 45, 45, 90-degree triangle. This is the first of our special triangles. Second, let's look at a 30, 60, 90 triangle. To derive this one, I'd like you to consider an equilateral triangle where all of the angles are the same. They're all 60 degrees to begin with. And we're going to drop a perpendicular bisector through the middle of this triangle. This becomes a 90-degree angle. This is 30 degrees. And we know for the equilateral triangle that all of the sides are the same because all the angles are the same. So we have side length s, and if I measure from here to this bisector, this will be s over 2. Looking at this 30, 60, 90 triangle on the left-hand side here, there's a missing leg. And so let's solve for that missing leg using the Pythagorean theorem. X squared plus s over 2 squared equals s squared. I get x squared plus s squared over 4 equals s squared. If I subtract s squared over 4 from both sides, I get x squared equals 3/4 of s squared. Here I take a square root, and I see that x equals root 3 over 2s. That's the missing side of our triangle, root 3 over 2s. Once again, sine, cosine, and tangent of this triangle, of the angles on this triangle, will be the same regardless of what the side length is. And so let's choose a side length of 2 in order to clear the fractions in these expressions. So I'll say the hypotenuse is 2. That makes this side length 1, and that makes this side length square root 3. This is our 60-degree angle, this is our 30-degree angle, and of course we have our right angle. This is the second of our special triangles. I recommend memorizing these two triangles and their corresponding side lengths because they occur so frequently in trigonometric expressions. Now that we have the triangles, let's see how we can use them to evaluate some trig expressions. I want to evaluate sine of 60. Remember that sine theta is opposite over hypotenuse, so it's going to be square root of 3 over 2 from the 30, 60, 90 triangle. Second, I want to evaluate tangent of 45. Tangent is opposite over adjacent. So we look at the 45, 45, 90 triangle. Opposite over adjacent is 1 over 1. So tangent of 45 degrees is equal to 1. Cosine of 45 degrees, that's adjacent over hypotenuse. Looking at the 45, 45, 90 triangle, that's going to be 1 over root 2. So we have 1 over root 2. We often see this in its rationalized form represented as root 2 over 2. Finally, cosecant of 30 degrees. Secant is the reciprocal of sine of 30, so it may help first to think about sine of 30 degrees. That's from the 30, 60, 90 triangle. That would be 1/2. So sine of 30 degrees is 1/2, which means cosecant of 30 is the reciprocal, 2 over 1, or 2.